Hi 3-1, today I'll be going through your mole worksheet 3, 4 and 5. Okay, so for question 1 of your mole worksheet 3, you are actually tasked to draw two possible diagrams to represent 4 moles per dm cube. So as you can see on the left side, we actually have 2 moles per dm cube, basically 4 particles in 2 dm cube of solution. So if you want to get 4 moles per dm cube, there's actually 2 methods. The first easy method is to simply just double the amount of solute, right? So instead of 4 particles in 2 dm cube of solution, we can double it to have 8 particles. So do take note here that you need to have exactly 8 particles drawn. There will be no other possible answers. Then next, the second possible easy method is to simply just halve the amount of solvent that we use. So instead of 2 dm cube of solution, we use 1 dm cube of solution, and we retain the same number of particles. So in this case, you will be using 4 particles. Okay, next, for question 2 of your MCQ, do take note that the chemical formula of sodium sulfate is Na2SO4. So actually, when it ionizes in water, it will form 2 Na plus ions and 1 SO4 2 minus ion. Then in this case, we also take water molecules to be simply existing as water molecules, and water molecules do not ionize. So in this case, if we are comparing Na plus and SO4 2 minus, the answer will be just the Na plus ions will be in the highest concentration. Okay, so for next question, sulfuric acid has the formula H2SO4, so it will form 2 H plus ions and 1 sulfate ion. So 0.05 moles per dm cube of sulfuric acid will have 0.10 mole per dm cube of H plus ions. Okay, lastly, for question 7, I think quite a number of you have forgot that iodine actually exists in I2. It's a diatomic molecule. So for your mass number, for the molar mass of iodine, it should be 127 times 2. So the answer is actually 0.01 moles per dm cube. 0.01 mole. Then after that, we account it for in 250 cm cube of solution. So 1 dm cube of solution, which is just simply times 4, which is 0.04 moles per dm cube. Okay, I will not go through the rest of the calculation questions in detail, because I think most of you got the answers correct. Let's just skip all the way to this question here for burette reading. Okay, so do always take note that for burette readings, we have to always read to 2 decimal places, because we are actually able to read to half a smallest reading of 0.05 cm cube. So in this case here, like example, if I've drawn this rate meniscus level here, it's actually in between 23.3 and 23.4 cm cube. So in this case, right, we actually record this value as 23.35 cm cube. So as you can see, we are actually able to read burette readings to up to 2 decimal places. So in all your readings in the graph below, you have to record everything to up to 2 decimal places. Okay, so do take note of all these values. I think all these values, you should be able to get them correct. And if they are asking you to choose the best titration results, right, we actually have to choose at least two results that are plus minus 0.20 cm cube of each other. So in this case, the only 2 results that you should choose is the result 2 and result 4. Okay, so similarly, for your average volume that you calculate, it has to be in 2 decimal places, because you are using 2 values of 2 decimal places, and you're just simply obtaining the average. Okay, so in this last part, why the volume of distilled water the student adds to apparatus A does not affect the result of the titration, because it does not actually affect the number of moles of magnesium hydroxide in the conical flask. So you are essentially just diluting the magnesium hydroxide solution, but you still require the same amount of hydrochloric acid to neutralize the solution. Okay, so let's move on to let us move on to this question, the part B of this question. So in this question, for the molar mass of XOH, we actually try to give it in 2 decimal places or up to like 5 SF. Then afterwards, right, when we obtain the MR of XOH, we subtract 16 and 1. So you obtain like 39.25, then we actually round up to the nearest whole number to try to identify the identity of X. So if by looking at your periodic table, you should be able to deduce that it is potassium. Okay, so now let us move on to this last question here. So there's actually, I think most of you are able to get this question correct, but do take note that for your mole ratio here, please take note that it is actually MnO4 minus ion. So please remember your charge, then Fe2 plus ion. So it's not MnO4 to Fe. It's because you are comparing the ratio of the mole ratio of the charge of the ions. So we have to include the charge of the ions down. And afterwards, when we obtain this answer here, 0.1, we also actually have to compare mole ratio back for the Fe2 plus ions and Fe, so that we are able to obtain the mass of ion. So simply put, right, what this means is that one Fe2 plus ions was actually 1 mole of Fe2 plus ions was formed from 1 mole of iron. Yeah, so do take note to compare this last mole ratio to actually deduce the mass of iron. Okay, so now let's us move on to worksheet 4, more worksheet 4. So for limiting reactants, generally I'm quite happy that most of you are able to identify the limiting reactants in all the questions. However, do take note in this in limiting reactants, right, the writing of statements is actually very important to actually help us to justify. So you actually have to justify using statements well, why you are actually using the limiting reactant in your subsequent calculation when we are tasked to find like the amount of product that was formed. So you do have to explain, like, or sometimes you will have this amount, you are actually having this amount of excess reactant, however we only require this amount to react completely with the limiting reactant. So therefore that reactant, we are using the limiting reactant to compare the mole ratio in the entire problem. Okay, so do take note of the writing of your statements. Okay, so after every working, when we actually justify the limiting reactant, we always have to justify it with a statement at the end. Okay, so actually I've highlighted all the statements at the end so that you guys can take note, pay attention to it, and see how the statements were being written. Okay, so one thing to take note, for gases, right, just simply, okay, not for this question, let's see. Okay, like for gases like this, right, do take note, just try to use mole ratio is simply equals to the volume ratio. So don't you guys really don't need to go through one entire loop of trying to find the number of moles of a gas, then compare mole ratio, then multiply back by 24 dm cubed to find the mole of the required gas. So before that, right, we always write this statement for gases. So you can just simply write this statement. Yeah, after writing this statement for gases, mole ratio equal to volume ratio, you can simply compare the mole ratio, and then you can show the marker that you understand that the mole ratio is simply the volume ratio when we are comparing two gases. Okay, then afterwards at the end, you still need your statements, justify which is the limiting reactant, and try to explain it in words so that it's clearer to the marker. Okay. Okay, then other than this, let me see. Okay, so for this question here, there's actually two ways to actually show that at the end of the experiment the solid contains unreacted copper. So the first method that I highlight that is on the left side, you show that the number of moles of copper is actually larger than the number of moles of copper 2 oxide that was being formed. So that this basically, and afterwards, right, you guys have to justify it with a statement. So after you show me these two values here, you need to use statements and explain it in words what these two values actually represent. So yeah, do take note of that. So there's actually a second method to justify that the solid left at the end of the experiment contains unreacted copper. So there's a second method. You can actually determine the theoretical yield of copper 2 oxide. So after you obtain this value 0.015625, we multiply by the the molar mass of copper 2 oxide. We obtain this value of 1.25 grams. So actually you can show to the marker, you can show that okay, the actual yield of 1.07 gram is actually less than the theoretical yield. So this actually means that there is unreacted copper left. So you can justify in terms of number of moles of reactant and versus product, or we can justify in terms of mass, like theoretical yield and actual yield. Okay, so for this question 9, I think a lot of you after you justified the limiting reactant here, you guys didn't write your statement. So remember for every limiting reactant problem, we have to write the limiting reactant statement to show that why we are using the limiting reactant as the basis for comparison of the mole ratio. Okay, so for this question 10, I think a lot of you either you accounted for the mass of the unreacted water, and then you forgot about the calcium hydroxide, or you only simply calculated for calcium hydroxide and you have forgotten about the unreacted water. So do take note in this chemical equation here, there's actually there will be this product form, and also there will be excess water, because in this case calcium will be the limiting reactant. Okay, so do take note of these two substances that was being left at the end of the reaction. Then you have to add both masses together. Okay, so let us look at question 11 and 12, the two MCQ questions in mole worksheet 4. So if 0.02 mole of sodium reacts with 300 cm3 of chlorine gas, what is the volume of excess chlorine gas? Okay, so first step, find the number of moles, right? For limiting reactant problems, find number of moles of both reactants. So 0.02 moles of sodium. Then for 300 cm3 of chlorine gas, it's I did the calculation here. It's 0.0125 moles of chlorine gas. So if based on proportion, right, you can actually deduce that 0.02 mole of sodium will actually only require 0.01 mole of chlorine gas. So chlorine is indeed in excess. So to find the volume of excess chlorine gas, we just do this subtraction. So 0.0125 minus 0.01, then afterwards is multiplied by 24,000 cm3, so that you actually obtain this final answer of 60 cm3. The answer is just A. Okay, so now let's move on to the last question of mole worksheet 4. Okay, so you're actually given 30 cm3 of H2 gas and 20 cm3 of nitrogen gas. So you just have to do your have and need. So you'll realize that 20 cm3 of nitrogen gas would require 60 cm3 of hydrogen gas. However, there's only 30 cm3 of hydrogen gas available. So in this case, right, hydrogen gas is actually limiting. So if hydrogen gas is limiting, 30 cm3 of hydrogen gas will require 10 cm3 of nitrogen gas. Okay, so in this case, we actually take 20 minus 10. So you'll realize that there's actually 10 cm cube of N2 gas remaining at the end, while because hydrogen gas is limiting, hydrogen at the end of the reaction it should be completely used up. Then by comparing mole ratio, the amount of ammonia gas formed, it should be 10 times 2, so you should form 20 cm cube. So at the end you should get this answer. Final is 10 cm cube of nitrogen gas left, hydrogen gas completely used up, while 20 cm cube of ammonia gas was formed. So the answer is just B here. Okay, so that's it for mole worksheet 4. Let us move on to the last mole worksheet that I'll go through, mole worksheet 5. Okay, for mole worksheet 5, for the most of the calculation questions, I'll actually skip them because most of you are able to get them correctly. I'll just focus on some of the questions that you guys had some errors in. So do take note for this column here, it's pretty standard. Remember for titration reading, we always take final burette reading and subtracting the initial burette reading. And all your burette readings must be in 2 decimal places, so just always take note. Burette readings always in 2 dp. Then similarly for the best titration result, we choose 2 results that are plus minus 0.20 cm3 of each other. So in this case, if you are looking at titration results 1 to 4, we will just take titration result 2 and titration result 4. Okay. So similarly, your average volume calculated must be in 2 dp, 16.80 cm3. Okay, let's look at part B1. Part B1, the number of moles of KMnO4 is simply here, right? Because we have 2 values here. We have 16.90 cm3. We have 0.005 moles per dm cube of KMnO4. So just multiply them together, we'll obtain this value here. Okay, so using this value, they say 5 moles of Fe2 plus ion will react with 1 mole of KMnO4. So just compare the mole ratio. So Fe2 plus to MnO4 minus. Okay, it's a 5 to 1. So we can just simply multiply by 5 here. Okay. So remember, for all your intermediate workings, if it's non-exact, we leave it to up to if there's a non-exact 3SF answer, we actually leave it up to like 4 to 5 significant figures if possible, so that in the subsequent calculations we don't keep using like rounded up values, which actually affects the final answer. So from here, we actually the final answer, we leave it in 3 significant figure, but we will use this 4225 as the value to use in our subsequent calculations. Okay, so I think for part 2 is quite straightforward. Let's move to part 3. So a lot of you here in 5 tablets, you guys just multiply by 5, which is actually wrong. We actually multiply it by 10 because whatever that was present here in the Fe2 plus ion, it was actually in the pipetted solution, right? 25.0 cm3. We pipette 25.0 cm3 of solution. So this was the number of moles of Fe2 plus ion that was present in 25.0 cm3. However, in the 5 iron tablets, right, that we initially crushed, it was actually used to form 250 cm3 of solution. So actually, we have to multiply by 10, right, to actually obtain the total number of moles of Fe2 plus ions that was present in the 5 iron tablet initially. So do take note here, we actually have to multiply by 10 using that value 4225. So we should form 0.0, the total number of moles of Fe2 plus ions is 0.004225. Then we multiply by the AR of iron. We should able to get this value of 0.234 grams. It's actually 2336, the exact answer, but for the final answer here, we'll just use the 3SF value. So if you realize in this question, you actually require to use values from the previous part to do continuous calculations all the way to the end. So for the subsequent part, we will actually use 0.2336. Okay, so they are actually asking you to calculate percentage by mass, right? So 0.2336 we just divide by the total mass of the 5 tablets that we use, and the final answer should be 12.8%. Okay. Okay, let us move on to the next question that I'll go through. All these are generally fine. Okay, let me see. Okay, let us move on to question 14, the only MCQ question in this worksheet. Okay, so you are actually given this reaction here, the heating of ammonium nitrate, thermal decomposition reaction. Then you are using 80 grams of the impure sample to heat, and then you actually obtain 27 grams of water. So if you want to find percentage purity, we actually work backwards. So using 27 grams of water, we determine the number of moles of water that was formed. So it's given here, 27 out of 18 mole. Okay, maybe let me write the units. So do take note to include your units at the end. So this is the number of moles. Okay, we should get this 27 out of 18 moles of H2O that was formed. So afterwards we compare the mole ratio, and we are actually able to deduce the number of moles of ammonium nitrate, which is 27 out of 36 mole. Then if you want to find the mass of ammonium nitrate in the impure sample, we just multiply it by the molar mass of ammonium nitrate, which is 80. So in the end, your answer that you get should be 80 times 27 out of 36, which is option B. Okay.